Hello and welcome back to the Polaris School of Quantum. Today we are looking at a company called Quantum Source, and if you have never heard about them and if you are interested in what they are doing in the space of photonic quantum computing, then stay tuned for today's video as we are diving into Quantum Source. As per usual, get yourself something to drink and get yourself comfortable. We are starting right away on their website. So here we are. It says bringing fault-tolerant quantum computing to light. Quantum Source is on a clear path to the most powerful, cost-effective, practical quantum computer. So how does that work? I think we've talked about other companies in that space before that are planning to use light quanta, so photons, in order to build operations that can then map onto a quantum computer. In the background, we see this huge chip with a lot of, let's say, or this huge wafer with a lot of little chips on it. And I think this is part of, let's say, the proposal here or of the business idea to build a chip, but we will learn a little bit more as we are moving down into the company. So, practical quantum computing. The realization of large-scale fault-tolerant quantum computers depends on the ability to minimize the overhead required for quantum error correction. With quantum error correction, the rapid accumulation of noise and errors prevents the implementation of long algorithms that are the holy grail of quantum computers, like the Shor factorization protocols or complex chemical simulations for the pharmaceutical industry. So I think we've talked about this before. The quantum computers today, we are in the so-called NISQ era, so noisy intermediate state quantum computers. The qubits are collecting errors, and it's not super easy to correct for that. It's a whole research area in itself, which is called quantum error correction. But the gist of it is you need a lot of physical qubits to generate a few number of what we call logical qubits that are not prone to these errors that are being accumulated over time. To build proper algorithms, you need these corrected or you most likely need to these corrected qubits though, because in order to build those you need to run a lot to build those algorithms you need to run a lot of concurrent operations on your qubits, and these need to be error-free. Examples for this are the Shor factorization algorithm, which is relevant for cybersecurity, which is basically could break today's encryption, but also other ones in the space of the chemical industry mentioned here, so pharmaceutical industry, where you basically try to use quantum computers to emulate or simulate quantum systems. Back to the text. So building such fault-tolerant quantum computers requires moving from the level of hundreds of qubits to millions of qubits. That's what I said before, right? So photonics offers the most promising route to achieving large-scale fault-tolerant quantum computing, as it allows for rapidly generating multiple photonic qubits using simple optical fibers as a huge quantum memory. However, meeting the scalability and cost efficiency requires of commercially viable machines is a significant challenge for existing technologies. Quantum Source aims to address this challenge using the photon atom gate architecture that offers a major change of scale and other key benefits, setting it apart from currently available quantum computing technologies. So our quantum architecture, our technology enables large-scale fault-tolerant, commercially useful quantum computers based on a novel approach of coupling photonic qubits with atomic qubits. Quantum Source harnesses single atoms trapped on a photonic chip to both generate single photons and to implement quantum photon entangling quantum gates, facilitating the construction of complex 3D cluster states that are at the backbone of error correction codes. The deterministic nature of the gates minimizes the need for costly and complex feed-forward and switching operations that are necessary in other quantum computing approaches. So again, what is all of this about? I can, let's say, not explain the exact reasons, but let's think about it on a high level. So if you have a quantum computer where you encode information in atoms or in ions, let's say in ions, you're usually using states of those ions. Could be vibrational states, could be, let's say, electronic states to store information. Usually you use electronic states for that. So you excite an electron, for example, into an upper level, and thereby you are creating a quantum state that is differentiable, and therefore you store quantum information in there. That can be stored usually for, let's say, quite a long time. So it is stable, it's a more or less stable state, and it has a certain lifetime associated with it. And that basically is in your favor because you can then do your operations. You can even shuffle those ions around physically and do stuff with them with this information being preserved. If you're now using light quanta, so photons, they are basically traveling at the speed of light, and it's incredibly hard to store this information. Now, if you want to do error correction, you need to more or less figure out a way to store parts of your information in some, let's say, parity or in some other state, or you need to be able to have another state to figure out if your original state has been affected by an error. So you need to somehow store this information, and that becomes very complex when it comes to photons, because still you can entangle them like with normal gates, but let's say storing this information is kind of complex. And here, as far as I understand, you try to build, let's say, an approach where you have the best of both worlds. So you're using on the one side these photonic qubits, but then on the other side those atomic qubits, and you are converting the quantum information from one to the other depending on what you need, what is, let's say, preferable for the let's say operation that you're trying to do, and this with the goal in mind to be able to create an error correction. Here is the leadership team. There's some note as well on the investors. So you see, for example, Dell Technologies Capital in here, as well as Eclipse and other ones. And then that's everything about this side. Now let's quickly look at the approach. So it says taking photonic quantum computing to new horizons. Large-scale fault-tolerant quantum computing is best achieved through photonic approaches. The challenge lies in generating entangled photonic states with current technologies relying on costly and complex probabilistic methods. Quantum Source utilizes a proprietary technique for creating entangled photonic clusters, order of magnitudes more efficient than existing methods, dramatically reducing the complexity and cost of quantum computers. A scalable architecture for practical quantum computing. In contrast to current probabilistic approaches, Quantum Source harnesses single atoms trapped on a proprietary photonic chip to allow deterministic photon generation and entanglement. Our unique approach results in a significant change of scale compared to all other implementations, which makes our system substantially more scalable, compact, and simpler to control. The entire Quantum Source system also operates at room temperature, which further reduces the complexity and footprint of our solution. Together, these advantages will lead to quantum computers with a price point, ease of installation, and footprint that make them a realistic option for businesses, delivered through flexible deployment models, including on-premises and quantum computing as a service, QCaaS. With our practical approach to quantum computing, we aim to make a real impact that will disrupt industries such as healthcare, energy, transportation, and financial services. And I mean, we know these industries also from other companies that are targeting quantum computing. Here's something about the scalability, feasibility, and manufacturability. And then the idea is, harnessing the power of light. Quickly on the technology side of things. So how does it actually work? Enabling large-scale fault-tolerant quantum computing by making the most challenging part of photonic quantum computing computation deterministic instead of probabilistic. So Quantum Source provides a viable route towards constructing large-scale fault-tolerant server rack-sized quantum computers, and Basically, the magic source here is this cavity QED, which they are making use of. So cavity quantum electrodynamics is the field of science that deals with enhancing light-matter interactions by focusing light into micron-scale optical resonators. In such tight confinement conditions, the electric field associated with a single photon is strong enough to allow deterministic interaction even with a single atom. So quickly on that, what is a cavity? Think about a classical laser. Lasers are devices that have been invented in the first quantum revolution. You are basically using a quantum excitation and you're triggering it, and then it creates a photon. Now, if you have a crystal of these materials that create those excitations, you can create a lot of photons. And what you're doing is, in order to build a laser, you are coupling them in a cavity. A cavity is a place where you have two mirrors, so that now every photon that is generated basically bounces off, goes to one mirror, bounces off, goes to the other. So they're basically pinging back and forth. And thereby you create a state where there's, let's say, electromagnetic resonance. So similar to when you have a sound wave that is propagating within a pipe, you are creating this, let's say, standing wave in a cavity. So you're creating spots where the magnetic field is high and other ones where it's low. Practically, the same is happening in your microwave. You have a magnetron which is producing microwaves. Microwaves are electromagnetic waves, so they are light. And they are now going through your microwave. So inside your microwave oven, you have microwaves, electromagnetic waves that are going back and forth. They're being reflected by the metal. So the metal acts like a mirror. And now they are bouncing back and forth within your microwave. Actually, the microwave, the wavelength, is long enough so that it is basically in the centimeters range. So you could even measure the size of the wave. And that basically creates the problem that within this microwave, you have certain areas where the amplitude of your electromagnetic wave is very strong and other ones where it's basically zero. Why is this a problem? Well, if you want to heat up your food and you put it inside and you just turn on the microwave, it will basically cook the food in certain places and other places stay cold. That's why in almost every microwave, except of, let's say, modern specific different technologies, you have this rotating plate which is like spinning your food all the time. That's basically to make sure that every single part of your food once goes through a place where it is actually experiencing this strong electromagnetic field, which basically brings the water molecules to vibrate inside your food, and that heats up your food. If you would take out the plate from your microwave and you put a piece of cheese, maybe you put it on a cutting board or something, into your microwave and you turn it on, you will see that the cheese melts in some regions and other ones they don't melt. That's basically because of the length of your microwave. Now, thinking about optical light, like lasers for example, the wavelength is much, much shorter. Usually it's in the hundreds of nanometers. So like 400 nanometers, 800 nanometers, things like this. So in order to create such a cavity where you know exactly where you have a high magnetic or a high electromagnetic field and where not, you have to shrink down the cavity a lot. So in a laser, it's more or less a random process because the cavity is quite large. But once you start shrinking it, you can now say where the electromagnetic field is going to be strong and where it's going to be weak. And now if you put a atom exactly in the point where you know that the electromagnetic field is going to be strong, you don't need a lot of photons to excite it anymore. Even a single photon, according to what is said here, might already be enough to excite this to excite this atom. Think about it like a rope. So you could have, I will take a cable because it's right next to me. So this is your wave now, and if you have the cavity, it basically means that you have fixed ends here. So now you could have a wave like this, which is going up and down and up and down, and then you have exactly in the center of your cavity, in the middle, you will have a very strong electromagnetic field. And if it's now becoming longer, you have different modes of these swings that can actually happen. So that's how you kind of know where you have the regions of high electromagnetic response. And that's where you have to put the atom so that you can excite even with a single photon, according to what we see here. Good, let's move on. So deterministic photon generation and gates. Once the condition of cavity QED are attained, high single atom cooperativity, a host of valuable atom mediated quantum operation opens up, including single photon generation and photon atom quantum logic gates. Every protocol cycle begins and ends with a verification stage that ensures the presence of a single atom in the trapping site. If not, that site is disabled until a new atom reloads and the atom's electronic state is correct. So you get the atom into the cavity, you check if this atom is really available in the cavity, and then you can route a single photon in there. You can transform this photon into an electric state of this atom. So this is this photon atom quantum logic gate. So you now put the photon into the atom. You can then do some gates on this. You can transform it. You can change things. You can also shift it back and forth or store it, whatnot. And then there's the single photon generation. So once the atom decays back to its ground state, it generates a photon, and that can then be used for something else. So we see these two things. So single photon generation with only one atom trapped and high cooperativity. The excitation of an atom is guaranteed to generate exactly one photon into the resonator's mode. And then the photon atom gates. So in contrast to the atoms in the photon generation sites for our entanglement protocols, and the other atom trapping sites are tailored to use a 3-level alpha configuration of the atom rubidium at 87. In this configuration, optical fields can tune the atom to perform one out of two native gates. The swap, which is the quantum qubit is exchanged between the photon and the atom, and the control phase or ZZ, in which a pi phase shift is implemented only when both qubits are in the one state. So these are the, let's say, operations that you can then perform, and then quantum source architecture removes the barriers of practical quantum computing using deterministic quantum interactions between single photons and single atoms. And then on top of that, you can run the protocols, right? So by repeatedly implementing short multi-photon protocols in each side, a small number of trapped atoms on each chip can generate an entangle the very large number of photons required for fault-tolerant photonic quantum computing. The deterministic nature of the gates minimizes the need of costly and complex feed-forward and switching operations that are necessary in other implementations. And then there are also papers and tutorials available here as well. And then building block. So I guess this is now the, let's say, overall architecture. So you see there's the scalable architecture, the building block inside the system, and the science. So let's start maybe with the science side. So this is what we've seen before, right? Here you see the rubidium, and you see the photon generation and the gates that you can run on top of it. So deterministic entanglement. The breakthrough behind origin, or caps lock, is based on cavity quantum electrodynamics, the physics of how individual atoms interact with single photons, and confined inside high quality optical resonators. When a single rubidium atom is positioned near a high quality optical resonator, something powerful happens. The photon's electric field becomes strong enough for long enough time to interact with the atom deterministically rather than probabilistically, which means that each photon can be generated and entangled on demand with near perfect efficiency. And that's what you see here, right? You have the rubidium atom here. You excite this cavity with a laser beam from above, and that basically generates you this single photon, which then goes into this loop here. Can then entangle it with another rubidium atom over here via this cavity, and then entangle or whatnot, do your quantum states. Here you see an example for a Hadamard gate and then some CNOTs. So the atom acts as a quantum mediator, creating the nonlinear interactions that photons alone cannot achieve. The result is a stream of high quality entangled photons, cluster states ready to be stitched into large-scale array of quantum logic required for fault-tolerant quantum computing. Then inside the system, you see the laser, you see the rubidium cloud over here, and then I guess the chip over here. So that's where the rubidium atoms come from. It says photonic chip at the core. At the heart of each origin unit is a photonic chip. Below the chip, a cloud of rubidium atoms is held in vacuum. Precisely controlled laser beams guide individual atoms to designated trapping sites where they interact with high quality optical resonators. So I guess the chip sits in the same chamber here with the vacuum, and you can use the laser to basically guide with maybe something like an optical tweezer, a single rubidium atom into a specific position of this photonic chip. Then the building blocks. Nice animation here. So now you see the vacuum chamber inside the rack. So introducing origin. Origin is a deterministic photonic cluster resource state generator, the essential building block for photonic quantum computation. Where other photonic cluster state generators rely on probabilistic processes that require about 1 million of attempts for each photonic qubit, origin takes a fundamentally different approach. By combining atomic and photonic qubits, each unit generates entangled photonic clusters with unprecedented efficiency, approximately 4 orders of magnitude better than probabilistic methods. There's also a video available here. The result, a system designed to fit in a standard server room rather than one factory floor, the size of a few football fields. No cryogenic cooling, that's referring to solid state systems. No specialized infrastructure, just room temperature operation with the reliability required for practical deployment. Okay, and then the scalable architecture. So once you have one of them, you can basically scale them. So modular quantum computing, practical quantum computing requires millions of qubits working together at scale that demands a fundamentally different approach to system architecture. Rather than building one impossibly large machine, origin units work together. Each unit generates small clusters of entangled photonic qubits which are then stitched together into larger quantum structures. This approach means computational power that scales with the number of units deployed, and that's basically what you see here. So you can stitch them together via these probably photonic fiber connectors and basically create a bigger quantum system. As you know, with every qubit that you scale up, you more or less double the power of your system. So it becomes very quickly, very efficient and very powerful when you can do something like this, which is not the same for every type of technology out there. Let's quickly check here. So the customers, I guess, are in scientific and government and business. Okay, we know that. I'm not going to go through all of these resources. I mean, there's a lot here. I'm just saying I'm recording this in April 2026. The last one that I see here in the news section or in the featured section is from September 2025. So still, I guess, more or less up to date. Maybe not the latest news, but not also completely outdated. And there's also some report available here as well. As per usual, let's also quickly check out about the company itself. So about us, Quantum Source is on a mission to make quantum computing a practical reality. Our novel architecture designed around chip-based photon atom gates provides a clear path to the most powerful fault-tolerant quantum computer. Our unique technology enables deterministic generation of photons and entangling gates, removing major roadblocks such as scalability, complexity, and cost efficiency. Founded in 2021, our journey is backed by 2 decades of research at the Weizmann Institute of Science and built upon recent breakthroughs in photonic technologies. To date, we've raised a total of $77 million from top-tier investors. Today, our team comprises 57 multidisciplinary experts, including 6 professors and 25 employees with PhDs or postdoctoral research experience from leading universities worldwide. Committed to out-of-the-box thinking, our team finds creative solutions to long-standing technological and scientific challenges, paving the path toward practical and affordable quantum computers accessible to a wide array of audiences. And here we see the management team. Again, we not only have the technical people, but we also have, for example, a VP of human resources here. There's a whole board of directors and, of course, mentioned also the investors. I think they are doing probably something very interesting. I think this idea of using the rubidium and combining it with the photonic chips is for sure very interesting. Let's see if it basically guides them towards the way of scaling up even further, collecting more money and eventually, let's say, scaling their whole approach, or if we will see, similar to other areas of quantum technology, that there will be some consolidation happening in some company that is maybe a little bit earlier on in the photonic trajectory is trying to buy this technology that they make. But for sure, from my point of view, something interesting to keep in your eyes or to keep on the radar. I hope you like this video. If you want me to do more of those videos, make sure to give it a thumbs up. And in case you can hype the video, also make sure to hype it so that even more people can see it. With that, I thank you for your attention all the way to the end of today's video and look forward to see you in the next one. Until then, bye-bye.